Welcome back, Saxon Advanced Mathematics / Algebra 3. We are in Lesson 14. We're going to refresh our memories on SOHCAHTOA, sine, cosine, tangent, and the inverse of the sine, cosine, and tangent. So first of all, let's look at SOHCAHTOA and refresh our memory on what that means. This is just the mnemonic that we use to remember the three different formulas that we have. So the sine of an angle, which is the S, is equal to the opposite leg divided by the hypotenuse. And remember, these all only apply to right angles. C stands for cosine of an angle, and that's going to be equal to the adjacent divided by the hypotenuse. And TOA stands for the tangent of an angle is equal to the opposite leg divided by the adjacent leg. Now, when we don't know the degree of measure for an angle, what we usually have is the information here to complete this problem here. And then we use the inverse, which is sine -1, cosine -1, or tan -1 on your calculator. Once we've done this math, it backs it up and tells us what the degree of measure for the angle is when we use the inverse sine button. So remember that no degree of measure we use inverse, sine, cosine, and tangent. All right, you can probably write that a little bit neater than me on your notes. But if you remember that, if you can remember, the inverse is for finding the degree measure of the angle, and the regular way is when you have the degree of measure and you're trying to find either the opposite or the hypotenuse using the formula, then that's going to help you out a lot and help you to drop those numbers in and solve the way that you need to solve. So let's jump into our first example problem, 14.1. So here we have a regular triangle, or it's a right triangle actually, it's not a regular triangle. And this is side B, this is side A. We have a hypotenuse of 6, and we have a degree measure here of 36 degrees. So I'm going to rewrite SOHCAHTOA up here just because I like seeing it. It reminds me of what I need to do and how I need to do it. So I'm going to use sine to find B because it's looking for the opposite, right? So the sine of 36 is equal to B over 6. Now if I go ahead and multiply that out, I would multiply this side by 6 and this side by 6. Multiplying and dividing by 6 would cancel that. So that would cancel out. So 6 times the sine of 36 degrees is equal to the length of B. So first of all, before we do the mathematics, the calculation, let's agree to 2 ground rules for our answers this year. Rule number 1. Perform all calculations before rounding. I know you're going to be like, what? I don't know if I can do that. You can. What you have to do is just leave it on the calculator, right? Figure out a way to do it on the calculator before you round it down. Number 2, round to 2 decimal places unless otherwise specified. Now, if the problem that you're given says to round to 3 or round to 4, that's fine. Follow the directions that you're given. But if you're not given directions and we have problems like this that have long decimal numbers, by default, I want you to round to 2 places, okay? So those are our 2 ground rules for this year. So now we can do the calculations here now that we know how we're going to do them. So I'm going to pull up my calculator. Let me clear this out. And the first thing I'm going to do, order of operations says I should always do what is within the parentheses first. So I'm going to find the sine of 36 first. I'm not rounding it. I'm leaving it on the calculator. All right, so I found the sine of 36. Now I'm going to multiply by 6. So times 6 equals. Now I have a value. I have 3.5267, yada, yada, yada. I'm going to look at my second decimal place. Can I round it up? Yes, I can. So 3.53 is my answer. 3.53 is the value of B. Now, if you had rounded it sooner, you would end up with a different number. Now, it might be 3.54. It might be 3.52. I'm not sure which way it would round, but it would be 1/100th of a place off, 2, depending on the way that the numbers that you have to use. If you round after you do all the other calculations, you are much more likely to get the same answer that's going to be in the Jupyter system. The book does not round until after all calculations are performed. And then when it rounds, it typically rounds to 2 decimal places. So, if at all possible, follow the rules you're given unless you're given different rules to follow. Okay? Perform all calculations before rounding, and then when you're done, round to 2 decimal places, and you're much more likely to get that right. And this is the answer the book has, and it has that because we did this, or because they did this. So this is 3.53. I say that because, if you type it in the system, let's say you typed in 3.54 into Jupyter for this answer, I'm going to look at everything that you get wrong to make sure it's actually wrong. Because if it's actually right, like let's say you just formatted it incorrectly, like you put 2 spaces instead of 1, something that simple between your number and your unit of measure, something like that can make it, it wants to be identical, so it can mark it wrong. Little things, it can make it mark it wrong. 3.54 instead of 3.53, it'll mark it wrong. But if I see 3.54, right, I'm going to mark it right. But it's going to take time because I have to manually open it up and look at all the incorrect answers to make sure that they're actually incorrect. If you can do the same process that I'm doing, and you're much more likely to get the right answer. If Jupyter will go ahead and mark it right, that's what we want to happen, because not only does it save me time in the grading, but it also gives you the confidence to know that you're doing the problem right, and that you're not struggling with that. Because if you keep typing in the answer that you got because you rounded differently than I did, and it keeps telling you it's wrong, and you've done all the steps right, it's like beating your head against a brick wall. It's very frustrating and upsetting. And I don't want that for you. I want you to be able to type it in, go, yep, right answer, and move on. Okay, I want that for you. I want to take away the frustration as much as possible. And that's why I want us to follow the same rules when we do the rounding and the calculating of these problems. So, rule number 1, rule number 2, follow those, and you're much more likely to not get that frustration level. Okay? It's for your benefit as well as mine. So let's find A. We're going to use cosine for that. So again, we're going to say cosine of 36 degrees is equal to the adjacent, which is A, over the hypotenuse of 6. We multiply everything on both sides by 6 in order to eliminate the denominator. That cancels. So 6 times the cosine of 36 degrees is going to give us the length of A. So I pull up my calculator one more time. I clear this number out. Let me move over here so we can see. I am going to perform the calculation inside the parentheses first. 36 cosine times 6 equals, now I'm going to round. 4.85, can I round that? Nope, that's a 4. So we ignore all of this. 4.85 is my answer. 4.85 is the length of A. That is easy peasy, right? As long as we follow these rules, we should have fewer problems with typing in answers and getting them marked correctly this year. So I am asking you guys, for your own sake, to stick with that. I would write it down for sure. Write down those rules so you don't forget how to do that. So let's do example 14.2. So in 14.2, we are going to use the inverse because we do not have the degree of measure. Let me put all of this information in here. The hypotenuse is 7. This leg is 3. We don't know what this leg is. And this is M. We don't know. We don't know what that degree of measure is. So we are going to use, let me put SOHCAHTOA back up here, just so we have a point of reference. We are going to use the sine of M because we have the opposite, right? We could do opposite over hypotenuse to find this. So the sine of whatever M is equal to 3 divided by 7. Now, normally I would multiply both sides by 7. That's not going to help us. We can actually get some mathematics done with this. So I'm going to do the same thing I've been doing before. I'm going to follow rule number 1. 3 divided by 7 equals. I'm leaving it in the calculator. I'm not rounding it, all right? I'm leaving it. And now I'm going to click second key, inverse sine. Now, this is my final answer. This is the degree of measure that is right here. 25.376. Can I round the 7 up? Yes, I can. So 25.38 is the degree of measure for M. And that is all we had to do for this problem, was to find the value or the degree of measure of M. And that's it. Now, if we wanted to, we could find X, but we really don't have to use SOHCAHTOA to do that. We could use Pythagoras Theorem because we have some numbers where we can do that. So let's just try that out. 3 squared plus x squared, because those are our two legs, is equal to the hypotenuse, if I can speak correctly, squared. So 9 plus x squared is equal to 49. Subtract 9 from both sides, I get x squared is equal to 40. I find the square root of both of those. Now, this year, you have an option for solving. In fact, most of the time, I'm going to ask you to solve it. Very few times will I ask you, or will I not ask you to solve it. And typically that's going to be during a quadratic formula. You can solve the square root here. Now, if you were to just reduce it visually, you would come up with 2 times the square root of 10, which is fine. That's an acceptable answer. But it's just as easy to type 40 square root of in the calculator and get an answer. It's going to give it to you. I want you to start getting in the habit of doing that once you get this completely resolved, right? Because if you can do this mentally, like if this were 49 and you could just do it mentally and get 7, I would prefer you to do that because it's faster. Your brain is faster than a calculator. It takes you more time to type it in than it does to just know your multiplication tables, right? But if it's not resolvable that way, then use the calculator and solve it. I will take this as an acceptable answer, and I will also take this as an acceptable answer. 6.32 is X right here. However, it's going to depend on how the book gives it to me. So if the book gives me the decimal answer here, that's what I'm going to type in. If that's what's on the answer key, that's what I'm going to type in. But if your answer is marked wrong in the system, if you typed in this and I had the acceptable answer as this, I'm going to go back and look at the problem. I have a solutions manual. It shows me how it's worked out, and I'm going to follow it until I see something like this, and I'm saying, there's the square root, that's why. What would I resolve that to manually if I didn't use the calculator? And then I'm going to grade it on that merit. So if you had this typed in, I would get to that answer manually without using my calculator, and I would say, okay, I'm going to add this to that problem as an acceptable answer, because some of the problems, the way they're set up, will let me have more than one answer that's acceptable, that is possible. It just depends on how I've got it set up. So if you get it marked wrong and it's like this, I would highly recommend that you put that into the calculator and try the decimal answer. And if the decimal answer is marked correct, then you know that's what it is, right? You're doing it right. Don't get frustrated if you put this in and it gets marked wrong. Okay? Try to resolve it on your calculator using the square root function, and then see if you get that marked correct. In fact, you might want to go ahead and take that step to start with and see if it accepts it. And if it doesn't, then back up to this. Because more likely than not, in advanced mathematics, we're going to go ahead and resolve those square roots situations. All right, so let's talk about angles of elevation and depression. I'm going to clear the page. So with an angle, you have two different options here. Here is, let's say that this is this is a mountain, right? This is a mountain. And you're out in the Alps, right? You're a surveyor and you're measuring the height of the mountain. This is you over here with your surveying equipment. And you are looking up here, right? You're using SOHCAHTOA to find this number right here. You know what the angle is. You know what the distance is. But you need to find the height here. So you're using this to find the height. And that's great. We have specific names for these different things. When you measure up from a lower location, measuring that way, that is called the angle of elevation. And the reason it's important for you to know this is because it's going to probably be in a word problem at some point. What is the angle of elevation? Yada, 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 right? So that's when you're going to have to understand the perspective of the event, of what's going on. So the angle of elevation means you're looking up, you're measuring up, and this hypotenuse is called the line of sight. Okay? So the hypotenuse is the line of sight, whether it is the angle of elevation or the other one, which I'm about to show you. So let's say now you are, let's say you're on top of the mountain, right? And right next to here, there is water. And you need to know how far away this boat right here is. It's a little cute little sailboat. And you need to figure out how far away it is. So you can make sure that you have enough gas in your little motorboat to get there and capture it because it got away from the pier and you need to go get it and bring it back. Just, for funsies. So you're standing on top of the mountain and you see that. You're going to be measuring from here. Here's your height. This is your height. This is where it is. It's your altitude. This is your height here. This is your baseline. This is your line of sight. This is what you're looking at. So basically, line of sight is what you're looking at, and it's the hypotenuse of your right triangle. So it's just the direction you're measuring the angle at. So here you're measuring from the bottom up, here you're measuring from the bottom down. Does it matter that much? Not really. Not really, because it doesn't matter whether we measure from the top or from the bottom. The degree of measure is going to be the same right here. All that matters is it's going to illustrate the perspective that we're looking at it from, so we know what our point of reference is. So we know how to get where we want to be, right? We know how to draw it. We know if we need to include this angle here, if we can maybe draw a line across and flip it and use the corresponding angle, or what we call the complementary angle, because two angles together that equal 90 degrees are complementary angles. If we are going down and we're talking about vectors, then we might need to use the complementary angle. So that's the reason we need to know that. We need to know what our perspective is, what we're looking at, and that is going to tell us how to apply SOHCAHTOA appropriately to what we know and what we're given. All right, so let's do an example problem like that. So here's where we might use the angle of elevation. We have my little figure here. This is Eve. I love Eve. Eve is a sweet little girl. And she just happens to be 6 foot tall. Here in this picture, I'm not sure if Eve is really 6 foot tall in real life, but she's very tall and she's very sweet. And Eve is looking at this tree and she's trying to figure out how tall this tree is. Let me adjust this just a little bit because it's supposed to go right to the top of the tree. There we go. So now that's right. My drawing is accurate. So Eve knows that she's 6 foot tall, and she knows she's 200 feet away from the tree, and she's looking up at the top of the tree, and she's measured that angle of elevation, and that angle of elevation is 11 degrees. So she's wondering if she can figure out how tall the tree is by just having that information. Well, good news, you can. That's all you need. So what we're going to do is we are going to use the tangent here in order to find out. And we know that tangent, that's TOA, right? So that's going to be the tan of 11 degrees. And that is going to be the opposite, which is y, because here's the degree. That's the opposite. So y over 200. Now we know to get rid of the denominator, we can multiply both sides by 200. So this gives us 200 times the tan of 11 degrees is going to equal the height or the length of y. So we're going to pull up our calculator. We'll move it around so we can see better. And I'm going to do what's in the parentheses first. So 11, let me take off the inverse, the tan of 11 times 200 is equal to 38.876. Can we round 7 up? Yes, this is a 6, so we can round that up to an 8. So 38.88. 38.88 feet. Why did I write a Y? I'm losing my mind. 38 feet is the height of Y. Now, that's not the height of the tree. We need to find the height of the tree. So we add to that the height of Eve. Her line of sight is where we started measuring the height of Y. But now we need to get from here to here. And we know that that is 6 feet. So we're going to add 6 to this bit. So that is going to be 44.88 feet is the height of the tree. And that would be our answer for that. Notice I followed our rules. I did all of my calculations, and then I rounded to 2 decimal points. And that matches the answer the book gives us. So we are staying consistent with that. That's the most important thing, is to stay consistent with that. So let's do another one. Let's do 14.4. And let's do, this time, a degree of depression, right? Or an angle of depression. That's the way you say it. All right, so we have a little airplane here. Let me see if I can draw a cute little airplane. Here's this little spinny thing that's out front. So we have an airplane, and he is flying along like this. Pretty straight, I would say. And he is at a height of 3,000 feet. And he looks down and he noticed that there is an object 26 degrees at the angle of depression from him. So there's some little object. Maybe what he's doing is he's flying out over the water, and there's somebody in a life raft going, save me, I'm drowning. So he's got to radio that in and let somebody know where that person is. And in order to do that, he's got to find the coordinates. And he knows how to apply that distance to his coordinates so that he can let somebody know where they are. So we have a right angle here. I'm going to draw to that person here. And let's extend this. Let's make sure this all works out. Yeah. So there's that. That's where that person is located. And his angle of depression right here is 26 degrees. Okay. So if this angle of depression is 26 degrees, then we know that this angle is going to be 64 degrees because we just made a right angle to the ground, which would then turn this into a right angle. So these would be complementary angles here. So 90 minus 26 leaves 64. So this is the degree of angle that we're going to use to figure out how far away this person is. And this distance here is called S, and S equals what we call the slant height. Okay, so we're going to find that. So given 64 degrees and 3,000 feet, we can find out how far away they are. You know, if we have enough gas to go and pick them up, or do we have to call somebody else with a full tank to come and do that? And that's probably what he's thinking about, that little airplane in the sky. Can I save this person? Because, you know, pilots tend to be kind of heroic. So we're going to use cosine, and cosine is C-O. So, I'm sorry, not C-O, C-A. So, ka, toa. So that's C-A-H. That's why I have to say all three, because I'll do co for some reason because of cosine when it should be ka. So ka toa helps me remember to do it the right way. So that's going to be the cosine of 64 degrees is equal to the adjacent, which is 3,000 feet. That's why we're using cosine. So 3,000 divided by S, right? We don't know what S is, but we do need to figure out how to get S by itself so that we can solve for that. So the first thing we're going to do is we're going to multiply everything by S to get rid of that denominator. So we find out that we have S is equal to S times the cosine of 64 is equal to 3,000. That's great. We still don't have S by itself to solve. But now we have two factors, so we can divide by one of the factors, cosine of 64, on both sides. And then that's going to make this cancel, and we find that S is going to be equal to 3,000 divided by the cosine of 64. How do we do that on a calculator, Miss Tracy? Here we go. So what you're going to do, first we're going to clear it. But what you're going to do when you look at this, we know we have to find the cosine of 64 and divide 3,000 by it. So we're going to put that, if you have parentheses on your calculator, you can do that pretty readily. We're going to say 3,000 divided by, and I'm going to do the parenthesis, then I'm going to do 64 cosine parenthesis equals. That is going to hold that 3,000 for me and then divide once I find the cosine of 64, all in one step. So I don't have to find the cosine of 64 and write down that big long decimal, because remember, we want to do all our calculations first and then round. So using the parenthesis makes that possible. So definitely practice that to make sure that you can do it. And that gives us S as a value. First, let's see if we can round this. Yes, 51, that becomes 52. So 6843.52. So 6843.52. That is the slant height. That is the value of S. That is the distance that this plane is from this person out here in the water who is needing a rescue. And that is in feet. So let me write that out for you, what I did in the calculator. So on the calculator, I said 3,000. I pressed my division symbol. Then I did a parenthesis. And then I did 64. Now on my calculator, I have to do the degree of measure. And then I press the cosine button. And then I pressed the other parenthesis. And then I did the equal sign. And then that gave me this value. So it's quite possible that yours would be the same way. What matters is, does your calculator, first of all, have parentheses? Second of all, what order do you have to do this in? Some calculators want you to do the cosine and then the degree. Some of them want you to do the degree and then the sine button, whether it's sine, cosine, or tangent, second. So know your calculator. It's very important. If you don't know how to use your calculator, you're going to be lost. You really need to take some time and figure it out. And if you don't have the directions for your calculator, like, everybody throws that bit away whenever they buy the calculator. If you don't have it, guess what? Google. Just Google it. Get online. Google, how do I find the cosine on this type of calculator? And every calculator has like the type that it is, the top. Like the one that I actually use is a Casio FX 300 ES Plus, which is a kind of a mouthful. But if you'll type that in, just type in the type of calculator into the Google search, it will actually take you to instructions that you could probably download or print or just use as a reference. Bookmark it, and then you can pull it up whenever you need to. But do that. Figure out how to use your calculator for each new thing, and then make it a point to write that button series in your notes. You might want to even highlight that as, here's the calculator tip. Here's the calculator way. You need to know how to do that, because when you're taking the ACT or you're doing a test, especially when you get to college, you have that higher math that's higher than this. You're going to need to do that quickly, okay? You want to save as much time as possible, because the more time that you have to do the really hard stuff, the better you're going to do. All right, so that is the angle of depression. You have to think about where you are prospectively, because we saw that it led us to needing to use the complementary angle to the angle of depression in order to find that right triangle. Now, could we have possibly just drawn our right triangle this way? Absolutely. But it's a lot easier to look at it with the right triangle with the hypotenuse on the top. That's the way we're used to seeing it, and that's the way that makes sense typically. So, do it in the way that works for you, but that perspective means a lot. It helps us to see what's going on. So let's talk about vectors. Y'all thought we forgot about those. We didn't forget about those. So we remember that vectors look like this, right? This is your hypotenuse length, and this is your degree of measure of the angle of your line on the Cartesian coordinate system. In fact, I'm going to scroll down to the coordinate system here, make it a little bit easier on us to have that graph. So let's jump into this practice problem. We've got two, and we are going to look at a new way of writing these rectangular coordinates. So in Algebra 2, we would write the rectangular coordinates with an R or with a U. Remember that? And all that meant was, let me make a little system here for us to look at. all that meant was whether this was positive or negative, that told us where we were. So 3R, this was R, and that's because the positive was to the right. So it was positive, we would go 1, 2, 3. And then up was the y-axis, because when you're on the y-axis, you either go up or down. So if it was negative u, you would go below the x-axis, and if it was a negative r, you would go to the left of the y-axis. So positive 3 would be here, and a positive 4u would be up here, and that's where we would draw the point, and then we'd connect to the origin from that point, and that would be our vector. That would be how we would write it in rectangular format. Remember that? All right, so the only thing that's different this year is now we're going to learn the actual mnemonic for this, or the actual things. In higher math, we don't call this R. We called this R so that we could remember, and it would transition us to using the correct variable here. The correct variable here is a hooded I. That's what the correct variable is. And it was also to keep us from getting confused with the imaginary square root of -1. But that is not hooded. This one is. But that is what we need to put here instead of R. And for U, instead of U, we use J, the hooded lowercase j. So that goes here. Now, why this is like this, I have no idea. It kind of looks like an umbrella if you think about it. Why it looks like that, I don't know. Why they chose those, I have no idea. That's just what they do. So now when you see this, it's going to look like this. And that is still your rectangular coordinate. We just have to remember which one takes the place of the U and which one takes the place of the R. And the way we write this rectangular coordinate is like this. You can also write it in X, Y format, just like that. You take the sign here and the sign here, and you put your X here and your Y here, just like we would normally write a coordinate or a point in the Cartesian coordinate system. All right, very relatable. So the thing is, when we start typing in these answers in rectangular format, we don't have a symbol for hooded I or hooded J in Jupyter system. So I am going to request that you write it like this, like it's a point. When we ask for the rectangular version, you write it like that. Now there's the other version, there's the polar coordinate, and the polar coordinate is where we have the hypotenuse length and the degree of measure here. Whenever we have that, remember we have a hard time with this, underlining that or getting that symbol there. So just write whatever the hypotenuse length is. So let's say that maybe that length is, I don't know, 5. And then the degree of measure, let's say it's 50. What you're going to do is you're going to write 5/50 degrees. That's all you're going to do. You don't have to do any spaces. You don't have to worry about underlining it. Just write 5/50. I'm not going to ask you to go that one step further in the system when it's not necessary. I know what that is and what that means. All right. Okay, so now we have the all of the discussion stuff out of the way. Let's do a practice problem. Let's clear the page. Let's do 14.5. All right, give me a second. I'm going to draw this up here for us. All right, so 14.5 says that we need to convert -3i plus 2j to polar coordinates. So the first thing we do is we're going to plot -3, +2. So we have our point -3, +2, straight from these two here. That's this point right here that we've already plotted. And I used green just so you could see it better. this is our vector. So now we know what the legs are. We know that we have 3 here, 3 units here from the origin, and 2 units up from the x-axis. So we know what the legs of our right triangle are, and that's our right triangle. What we don't know is the degree of measure, so we'll just put our little theta symbol here to show that we don't know what that is. And we don't know the length of our hypotenuse, which both of those are required to find or to write the polar coordinate. So the first thing we're going to do is use Pythagoras Theorem to find r, because we need our hypotenuse in order to find theta, which is the degree of measure we don't know. So I'm going to say 2 squared plus 3 squared, because those are the 2 legs, that's equal to r squared. So 4 plus 9 is equal to r squared. 13 is equal to r squared. Square this, square this. So the square root of 13 is equal to r, right? Because this would cancel. All right, so we can leave it like that for now. If you wanted to, you could always, let's clear this. You could say 13 square root of, and then be 3.61 would be the value of r, because we've finished our calculation and we're rounding it to 2. So you could say 3.61 is equal to r. Either one of those is correct. All right. So if this is not accepted in the system, you can back up and use that one. All right, so now that we have that, now we can find the tan to find the degree of measure. Because remember, so ka toa is going to be the tangent of theta is equal to the opposite, which would be 2, over the adjacent, which is 3. So now we're going to do this here. So we have the calculator, and I'm going to do 2 divided by 3 equals, I'm not taking it out of the calculator yet, and I am going to apply the inverse tan to that, because inverse is when you find the degree of measure. So second tan 1, that's not right. I shouldn't have touched the equal. So let me clear that and back up. 2 divided by 3 equals, and then tan 1. That's where I stop. I hit the equal sign, it applies it again. I need to apply it again. It should stay where it is. So can I round this to 2? No, it stays 33.69. So this is equal to 33.69 degrees. Now I have everything I need to write this out as a polar coordinate. I am going to write that this is, because this is above the x-axis and it is clockwise, it's going this way, this is going to be a positive degree measure, because this is the way we want to go. We would go counterclockwise here. So this is a positive degree. So we would write the slash 33.69 degrees. And then this length is, however, this length is negative, I think. Let me see. That is not the correct degree of measure. Hang on. I goofed. This is the correct degree of measure for theta. But the way that we write the polar coordinate is going to be in regards to beginning here. We always have to do that. I forgot about that for just a moment. So we have to add this 90 degrees, and then we have to add the difference between 90 degrees and this little degree of measure here. So we're going to say 90 minus 33.69, And that's going to give us the degree of measure for this part right here. And that's the part that we want to use. So let's use our calculator. 90 minus 33.69. So we have 56.31. So 56.31 is right here. This is that degree of measure, 56.31. So we're going to add that to the 90. (146.31). So that is our degree of measure when we go this way. It's 146.31 degrees. Does that make sense? Okay. All right, this is indeed 33.69 degrees, but we start measuring here. So 90 all the way around to there is 146.31. All right, and our R is it's the length of this, right? So because it's going this way, it is positive. It's where the degree tells us it should be. So it is a positive, and you could say a positive square root of 13, or you could write it as 3.61 positive, 146.31 degrees. All right, so my hand is a little bit, I've been writing all day, so my hand's a little bit numb, so I got to shake my hand out. We typically only write this as a positive. The only time we write this as a negative is when we flip it and we go the opposite direction. Remember that? If it gives us a negative here, then we figure out where that would be and then we flip it. Right? Remember that. All right, so we find that when we write it like this, that is going to be written positive, 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 positive. Everything's positive because it's following the natural trajectory of the way we measure. And it's a positive length. It's not going backwards. If, on the other hand, let me use red to show you, we measured from this way around, then that would be written with the inverse degree here, and it would be negative. And that would be written 3.61 negative 140, or I'm sorry, it wouldn't be negative 146, it'd be negative 213.69 degrees, because 146.31 and 213.69 is equal to 360. When you add those two together, that equals 360. So this plus this gives us a full circle. That would be 360, right? So that's what the negative means. It means we started and we went clockwise instead of counterclockwise, which is the normal sweep of our vector. All right, so the other option, let me see, I might have to change color here. If we were to write, let's say we went, let me undo. That. If we were to flip this, right, and go this way, we found out what this was, and then we flipped the whole thing. This would actually be right here. So because it's this way, it'd be negative 33.69. So that would be negative 33.69. And then this would be on this side. So it would be negative 3.61 because it's on the wrong side. It's measured this way and that way. All right, and Yeah, that would be if it was like that. So then if we wrote this here, like we flipped it here, we measured all the way around, that'd be something different as well. So how you write it, you could write the same thing and write it a few different ways. How you write it tells us where it is and how you measured it. That's basically all I'm trying to get at. This is what I would prefer for you to enter. I prefer for you to resolve this if at all possible. Okay? All right, let's do one more. Let's try not to make this any more confusing than it is, because it is confusing. This is 14.6. This is the last example problem that we have. And here we are given the polar coordinates and we're asked to convert it to rectangular form. And these are negative. So we have a negative 13 here. And our polar coordinate is negative 253 degrees. So we have our coordinate system here. So there's that. So we always draw the angle first, as we show here. So our angle, if it's negative 253 degrees, then we're going to start here and we're going to go backwards, right? Not the normal way. We're going to go clockwise. So this would be 90. This would be 180. So that means up in here somewhere is 253. So we have to figure out what that is. So I'm going to say 253 minus 180. So if I do that on my calculator, 253 minus 180. That's 73 degrees. So from here to here, I'm going to go 73 degrees. It's going to be really tight. So I am going to try to draw, it's going to be about like that. Because if this is 45, right, we know this is 45, then about half of 45 would be like 22. So 45 plus 22, that would get us to 68. So it needs to be a little bit more than halfway to be about 73. So there's that. That's about 73 right there. That's a nice tight 73 degree angle right there. All right, and now that we know that this is 73 degrees, we could put that in here. This is 73 degrees because we are going to draw this line straight down from there. And that becomes our right angle. Okay. Now we have to put the length here of our hypotenuse, and I'm just going to write that. And that is negative 13. So if it's negative 13 at 73 degrees, it's going to be this way. So I've got to take this line right here, and I have got to drag it through the origin from the point that it's at, like that. So you see how that works? Because it's negative, it's now over here. And because it's always relative to the x-axis, these are the opposite angles, so this is 73 degrees. Actually, I'm going to write that inside here so it's a lot clearer. 73 degrees. And now this is 13, whatever that unit is. All right, so now I'm going to draw my right triangle up from the bottom. This one no longer matters, so I can scratch it out. We're not talking about that one anymore. We're talking about this one. This is actually what it is. So now that we have this degree of measure and this right triangle drawn, and we have the length of our hypotenuse, now we can start to figure some things out. So we're going to use cosine to find, this will be A and this will be B. Okay. And I guess technically, let me take that off. Technically, this is going to be hooded I, and this is going to be hooded J right there. So that's technically what it is. And this is going to be a negative hooded j because it is below the x-axis. It's going down. This is going to be positive I because it's to the right. So now we can figure out what those are. So let's use cosine. And so I'm going to write SOHCAHTOA up here just to remind myself of the proper formula. So we're going to do cosine. So the cosine of 73 is going to be equal to the adjacent, which is I, over 13, which is the hypotenuse. All right, so if I multiply both sides times 13, I get 13 times the cosine of 73 is equal to whatever my I value is. So I'm going to do that like I did earlier. I'm going to use my parenthesis, and I'm going to say, let me take this off of second. I'm going to say 73 cosine. I don't have to use my parenthesis, never mind, because it's just one operation, times 13 equals 3.80. So that is my I value. So I have 3.8 I, and that's a positive. So that's already by itself done. So now I'm going to use sine to find my j. So the sine of 73 is going to equal to the negative j over 13. Same thing, 13 times the sine of 73 is equal to the negative j. So I'm going to do that on my calculator. The 73, the sine, times 13 is equal. And can I round this? No, because the 1 isn't rounded, so it's 12.43. So 12.43, and it's a negative j, so that's j, but it's negative. So when I put those two together, this is what I have. That's my answer. 3.8 I minus 12.43 j. And you could also write it, when you type it in the system to turn it in, you're going to write 3.8 negative 12.43. That's the way you'll type it into the system. And that is in polar coordinate format. I'm sorry, rectangular. This is polar. This is rectangular. Alrighty? Alrighty, and that is all we have for lesson 14, and I will see you in lesson 15. Y'all have a great rest of the day. Ta-ta for now.